Hello, welcome to AP Calculus Lecture 2.6b, where we're doing our second of three lectures on related rates. If you'll get your notes out, we're going to start on the baseball problem in the middle of page 3. Okay, so it says a baseball diamond is a square with 90-foot sides. How fast is the distance between second base and the batter changing at the instant the batter is midway between home and first if he runs at 24 feet per second? So it's, a lot of times it's really easier to draw the situation. It's easier to see it. So let's draw a baseball diamond. Go ahead and put home plate in there. First, second, and third. Now the distance between each base is 90 feet. So I'm going to just put a 90 feet right there. We know what we're trying to get. So the batter is halfway between home plate and first. So I'm just going to kind of do a dashed line that goes from second base to the batter, and let's call this length L, and I'm going to call this distance between the batter and first base X, and we also know that the batter is traveling at 24 feet per second. So I think we've given a variable to everything that we need. So what we want is how fast is this distance L changing with respect to time, and of course it's getting shorter, right, as the batter runs. So we want dL dt. We know the rate of change of x. Okay, so dx dt is equal to 24 feet per second. So that distance between home plate and first base is changing at a rate of 24 feet per second. Now relate, it's usually a geometric equation. And what is this shape? Okay, the L is a hypotenuse of a right triangle here. So we would have L squared is equal to 90 squared plus x squared. And we always differentiate with respect to time. So that would be 2L dL dt. The derivative of 90 squared would just be 0, that's a constant, is equal to 2x dx dt. So solving for dL dt, I'm going to bring that 2L underneath. So it would be 2x dx dt over 2L. The 2's will cancel. So you have x dx dt over L. Now we should be able to figure out x and L. We know that x, it's when the batter is halfway. So x has to be 45 feet. We can get L because we know L squared is equal to x squared plus 90 squared, right? So L is equal to the square root of 45 squared plus 90 squared. All right, and that is equal to 100.6 feet. So now I've got enough to plug in and get the answer. dL dt is equal to x, which is 45, times 24 over 100.6. All right, and that is going to be 10.73 feet per second. All right, and we do have, I'm pretty sure, well, not on this one we don't, but on one of the homeworks we do have another baseball problem. So you'll want to refer back to this example. Okay, let's turn the page in your notes and do the next example. And that example is called the Blimp problem. Okay, and let's read through that together. It says, consider a blimp flying at an altitude of 800 feet. A mutant cowboy lassos the blimp, lets the rope out at 3 feet per second. How fast is the blimp traveling when the rope is 1,000 feet? Okay, so we'll draw a blimp. All right, got the control, the cockpit down underneath there. We know that the blimp is 800 feet in altitude. And we have level ground here. We've got to assume it's level ground. We've got a cowboy. So put a cowboy hat. And he's got some rope here. He lassos that blimp. Okay, something like that. And we'll call this R for rope. And we can call this distance X. So the rope is being let out at 3 feet per second. We want to know how fast is the blimp traveling. Okay, so the blimp is going this way, right? It's traveling horizontally. That's what we've got to assume. So what we want then, that horizontal distance is represented by x there. So we want dx dt. What we know is that dr dt is equal to 3 feet per second. Now we don't plug in all those other links like the rope is 1,000 feet. We don't plug those numbers in because those are changing numbers until after we take the derivative. Now this 800 feet is a constant, so it does stay as part of the equation, but this is also a right triangle. So we would have r squared is equal to 800 squared plus x squared. So if we take the derivative of that with respect to t, we have 2r dr dt is equal to the 800 squared, the derivative of that is 0, 2x dx dt. Of course, the 2's will cancel out. Dx dt, solving for that, is going to be r dr dt over x. Okay, bring that x underneath. The 2's will cancel. And there we go. This is the speed that the blimp is traveling. Blimp's going that way. What's the speed that it's traveling? Okay, we know that r is equal to 1,000 from the problem. So we should be able to get x because 1,000 squared is equal to x squared plus 800 squared. So this is a 6, 8, 10 triangle, so I can tell you x is going to end up being 600 feet. But you can go through that if you want to. So our speed, dx dt, is equal to r, 1,000. dr dt is 3 feet per second over 600. So the feet and the feet will cancel. You're left with a unit of feet per second. 3,000 over 600. That would be 5 feet per second. So pretty slow moving blimp. I guess that's why our cowboy could lasso it. Okay, the homework is page 146, 20, 21, 25A, and 25B. So I want to give you some hints on these. So for number 20, you're going to need to use the fact that H is equal to 3R and substitute 3R for H. Otherwise, you have too many variables in the equation. All right, looks like I'm running out of room for my hints here. Okay, 20. So for number 20, H is equal to 3R. For 21, you're using the cone equation again, right? The cone equation is given in the book, in the problem. All right, but in this case, the diameter is equal to 3h. So it says that the base of the cone is approximately 3 times the altitude. H is the height. So h is equal to the altitude. So you need radius, not diameter. So we know that radius is going to be 3h over 2. So you'll substitute 3h over 2 for r in this case. And then you can take the derivative. You don't have too many variables there. Okay, and then number 25A is a ladder problem. So look at that ladder example. 25B, you're going to use dy dt found in 25A. So you're going to have to use part of your answer from 25A to get 25B. And remember, the area of a triangle is 1/2 base times height. So in this case, that'd be 1/2 x times y. Okay, because y is the height and the base is x. Okay, so 1/2 xy. So you'll need to use that for your relate equation and then take the derivative of that with respect to time. Okay, so that's quite a few hints. 20 and 21, you'll have to think through those. I think 21 is one that, I generally have to work both 20 and 21 for my students every year. But do your best and try to get it. Give it a couple of good solid tries on there and see if you can get it without having to look at my solution. But if not, the solution will be there for you. All right, that's it for this lecture, and I will talk to you on the solutions video.